Hello everyone. In this video we will discuss physical properties of carboxylic acids. So physical properties so far what we have been discussing, two of them. One is your boiling point and another one is your solubilities. So we will discuss these two properties here for carboxylic acids as well. So let's recap. So what is a carboxylic acid? So carboxylic acid has a carbonyl group and then it has a OH group, right? So this is, and it can attach anything on the sides, right? So this is our carbonyl group. And this is our hydroxyl group. Okay, so what is so unique about the carbonyl group? So if you recap your aldehyde or ketone chapter, so you'll find out that this carbonyl is a polar bond right here. So because oxygen is more electronegative, so it should have a slightly negative charge, and carbon is going to be slightly positive charge. So this bond here, the bond between carbon and oxygen, is a polar bond. So I'm going to write this one down here. So this is a polar bond. So if it is a polar bond, so it could do a dipole-dipole interactions, right? So dipole-dipole interactions. So how about the OH group? So if you remember from alcohol chapter, hydrogen and oxygen, this bond is also a polar bond. So this bond is also a polar bond. In this case, who is going to get more electron? Oxygen going to get more electron. So it becomes delta negative and hydrogen becomes delta positive. So you have two polar bond in carboxylic acids. It's like if you compare to the alcohol, alcohol has only one, aldehyde and ketone has this one. But in carboxylic acid, you have both of them together. So what is so unique of this particular OH bond? OH bond can form hydrogen bond, and we know that hydrogen bond is the strongest. And what is so unique about the carbonyl? This one can form dipole-dipole interactions, right? So dipole-dipole bond, right? Okay, so let's do a comparisons of the boiling point. So always the rule, if we are comparing between same class of compound, longer the carbon chain, higher the boiling point. What is the condition apply? In the same class of compound. So like you cannot compare two different chains, two different sizes between two different class of compounds. Like you cannot compare between alkane or alkane versus alcohol unless they are of same size. So the molecular mass plays a big role. So in this case, so if we have this CO, usually you can write like this, COOH. So this is carboxylic acid. So boiling point of this one would be smaller than CH3, COOH. This one would be smaller than CH3, CH2, COOH. And this one would be even smaller than CH3, CH2, CH2, COH. So as the carbon chain increases, the boiling point increases. So this is the boiling point, low to high. All right. Okay. You can compare between two different class of compound only if their size are same, right? So we did this in the previous class where we had an alkane, and then we have an aldehyde, then we have an alcohol. So in this one, we're gonna add another one that is carboxylic acid. So obviously alkane is non-polar, right? So this is non-polar. So this is always going to have the lowest boiling point. Everything else is polar. So this is polar, this is polar, this is polar. So as long as the mass are comparable, then the boiling point is going to increase from left to right. So here is one example we're going to talk about. So butane. So this is butane. Butane is C4H10. So the molecular weight is 58, right? So butane versus, let's do aldehyde, propanol. Propanol. Propanol is, this is. So the molecular weight for this one is our 58 as well. And the alcohol is propanol. So this is OL. So this one is 60. So the molecular weight of this one is 60, and the comparable carboxylic acid with the similar mass is ethanoic acid. So it is CH3 COOH. So this is also 60. So now we can, so this is our ethanoic acid. Okay, so in this particular example, we can compare between different functional group because all of their molecular mass are same or similar. So it's 58, 58, 60, 60. So these are close by. So obviously the expected, what do you expect? Butane is non-polar. So there is, in this particular example, no hydrogen bond, no dipole-dipole interactions. So dipole. So obviously this one should have the boiling point the smallest, right? So the boiling point for this one is 0 degrees Celsius. Propanol, Al. So this one, obviously no hydrogen bond, but it can do, yes, dipole interactions. So obviously the boiling point for this one would be slightly higher. In this case, it is 49 degrees Celsius. Or how about alcohol? Alcohol is, it can form hydrogen bond, right? Yes, hydrogen bond. So hydrogen bond is the strongest, so it should have the higher boiling point as well. So the boiling point for this one is 97 degrees Celsius. How about carboxylic acid? So carboxylic acid, if we go back, it has both the group, right? So it has hydroxy group that can form hydrogen bond, and also it has a carbonyl group that can form a dipole-dipole. So there are two polar bonds. So this kind of make things stronger. So this one has, the boiling point is going to be even stronger. It's 118 degrees Celsius. So you could see, but the reason actually the reason this one has higher boiling point because it can form a dimer. So this one actually form a dimer. So what is a dimer? So here is what happens. So let's say this is CS3CO OH. Maybe I should use this CS3. Okay, I'm trying to draw this figure pretty. See. Okay, so you can see here oxygen is negative. So it would make a hydrogen bond with the nearby OH, and hydrogen here will form a hydrogen bond with the nearby oxygens. So these two things, the one on the left and one, both are the same molecule. So in reality, what's happening is you are making a, so this whole thing is called dimer. So the reason it's called dimer because it's combination of two molecules, right? So if it's combinations of two molecules, the effective number of carbon atom increases, right? So you got, instead of two, in reality, you got 1, 2, 3, 4. So you have 4 carbon atoms. So this molecule becomes a larger size. So instead of 60, the actual mass of this molecule, like effective mass, becomes 120. And we know higher the mass, the higher the boiling points, right? So because it can form, it has this two polar group, one is OH, another one is carbonyl. It could form a dimer, which is a much stronger interactions, and as a result the boiling point is increases. So it's kind of easier to visualize if you follow this pattern. No hydrogen bond, no dipole for alkane, so low boiling point. In this case you got no hydrogen bond but dipole-dipole interactions. In this case you get the hydrogen bond, which is the strongest. In this case you get the both, which is even stronger. As a result, the boiling point is higher. So carboxylic acid has always higher boiling point. Solubilities. Solubilities are pretty much straightforward. So solubility is it's most of them are soluble up to 5 carbon atoms. If it's 6, then it's slightly less soluble. So up to 5. So if you have 1 carbon atoms all the way till 5 carbon atom. 5 carbon atom is pentanoic acid, right? So up to 1 to 5, methanoic acid. Up to 5, they are all soluble in water. But beyond that, they're insoluble. Like 6 carbon atom is slightly soluble. Anything beyond that, it's going to be insoluble. If you have benzoic acid, this is a carboxylic acid, but it has a benzene ring as well. So this benzoic acid, I'm going to draw the structure here. Remember the benzene ring? Benzene ring is, you have alternate double bonds and then you have a carboxylic acid attached to it. So you can write like this or you can write like this. If you have a circle in the middle, that's also becomes benzoic acid. This is also slightly soluble, just like 6 carbon atoms. All right, so let's stop here.